Earlier in the semester, I promised you that we would get into more impressive loop invariant proofs. So this will be our first example of a much more useful version of doing a loop invariant that's not just, a loop that's trying to sum something up. So let's use a loop invariant to prove the correctness of Dijkstra's algorithm. And this will look pretty similar to the proof that we've already done for Dijkstra's, but I did want to show you a loop invariant. So here's our theorem that we're trying to prove. Dijkstra's algorithm will find the shortest path from the start vertex to every other vertex on any graph with non-negative edge weights. That also assumes that a path exists. And as I mentioned in our first lecture slides on Dijkstra's algorithm, we're just going to make that assumption because it's always easy to check with a breadth first search or a depth first search if the graph is actually connected. All right, well, let's do a proof using a loop invariant, and let's use this as our loop predicate. At the start of each iteration of the while loop, the shortest path has been found for every vertex in the found set. All right, so that is our loop predicate, and it appears here. And here's the loop we have to begin with that we're trying to prove. And if you notice, the found set starts out empty. So what's our reasoning for the initialization condition? We can just say initially the found set is empty, so the invariant is trivially true. We can say that we have the shortest path to everything that's in the found set because there's nothing in the found set. All right, well, how about maintenance? For maintenance, we have to say start by sort of assuming that all previous iterations have produced the correct shortest path for all vertices in the found set. That's sort of the baseline you always start with, is let's assume that previous iterations worked. Don't forget that, a loop invariant sounds a little bit different and it's for a loop, but it really does much more resemble a proof by induction than anything else. So let's just say for purposes of contradiction that when a vertex u is added to the found set, that its path length is not optimal. So it's easy to show that that's going to be a contradiction. So let's just start with that. So what this means is that at the time that u is found, meaning the time we add u to the found set, we have to have some path to u, and later on we have to find some better path to u. So let me paint the picture for you. We have our found set, so those are all of the vertices to which we know the shortest path, and by our assumption here we can assume that those are all correct shortest paths. So we have our start vertex, and then we've already found the shortest path to A, B, and D. Well, we have a vertex u that we're going to add to the found set in this current iteration. And what our contradiction here says is that there's actually a shorter path to get to u. So for example, we could go from S to B to D to K up to u. That's one such shorter path. Well, that means we have to go through some other vertex. But since we only have positive edge weights, we know that this thing here has to be greater than or equal to 0, meaning that the only way that this path could be shorter is if this path, not all the way to u, so to k, is shorter than this path. But we know we're guaranteed that the path to u is the shortest path because that's exactly what we pop off the heap is the next shortest path. So that's a contradiction to our supposed unoptimality of our path going from S to B to U. So that contradiction shows us that our maintenance criteria is correct, or our maintenance condition is held, meaning that each iteration will add a vertex to the found set, and we will have the shortest path to that to that vertex. All right, finally, termination. Well, the loop terminates when the found set is equal to the set of all vertices. So all we have to say here is that, given the loop invariant, the shortest path to all vertices have been calculated.